Start recording. And okay, so let's get started. And I'm going to talk today about 4C and sort of the computer science aspect of things. And just before I get started, I wanted to point you to this website, talks.cam.ac.uk. And if you go to that website, you can go to the EEG group and you can actually see all the talks. And you can go to the get a calendar, and then you can actually subscribe to it. And thanks to Maddie who put everything in, you can download this and get into your calendar. So you'll see all the talks in the. So generally speaking, this is how we're going to run things for this term anyway. So we'll have a discussion up front. People will talk about what they did last week, a little bit more detail. And then we will have lunch here to be set up here rather than an SSO3, I believe. And then the speaker gets to talk, and then I'll finish my lunch later. Okay, so without further ado, let me, I should introduce Harriet Hannibal is working with 4C. I'm sorry I missed the other people's introductions, but we don't have, okay. All right, so today I'm going to talk about bringing scale and trust to carbon credits through computer science. And, okay, I can't get rid of that, so think over that, okay. And this is work I've been doing with Andrew Bartlett in zoology, David Cruz in plant sciences, Andrew zoology in computer science, and Tom Stoney also in zoology, and hence the themes here. And actually today I'm going to focus more on computer systems rather than any broad computer science, but actually specifically computer systems, because that's sort of my background. That's what I'm bringing to the table. I know that many of you, or perhaps all of you, have listened to Tom Stoney's talk earlier this week on Tuesday. So I'm going to not go through too much detail on the stuff that he already covered and focus on things that that he didn't cover. So, okay, we believe very strongly that we are in the middle of two major crises, the climate crisis and biodiversity crisis. Biodiversity crisis doesn't get as much mentioned, but of course it's just as important. And our focus is on nature-based solutions which address both. I have to get rid of this somehow. Okay. And these nature-based solutions such as forest conservation or reforestation, peatlands renewal, they solve the climate crisis because they're absorbing carbon dioxide from the air, so they're sequestering carbon dioxide. At the same time, they serve as places where we have, basically plants and animals able to live. Here. So mangrove plantations, mangrove harbors, many kinds of fish and crustaceans and things like that. So the broad category of nature-based solutions is something that CCI, the conservation folks in the David Attenborough building, are very interested in. And so one question is, how do you fund them? Because restoring nature takes money, and preventing people from destroying nature means they're foregoing income, right? These are people who are often quite poor. And if you tell them, no, you can't do this, you can't go and fish, what are they going to do instead? And so the solution to that is to give them money. Say, okay, please don't cut down the forest, here's some money. So you take the foregone income and you are going to give money instead. And so that comes in the form of what are called carbon credits. So a typical project is this one over here. We have forested land, and there's this bit of polygon observation space. And we observe that it has not been, it's not been deforested, and consequently, we can say that it's preserved. It's not been deforested. And so organizations such as Gold Standard and Vera, which are companies, they will create these reams of paperwork to attest that these projects have things like additionality, leakage, governance, co-benefits, which you've heard about from Tom, and they issue credits, right? And so I'm going to briefly talk about these 3 or 4 things. I'm sorry, but the problem is that these schemes are not really easy to quantify, they're hard to verify, they're hard to scale, and so that's the problem we're solving over here. Right? So what we're trying to do is to say, can we use our algorithms, our systems, our approaches to be able to come up with both scale and trust in carbon credits. Scale, that means that we can reduce the onboarding costs. So a project doesn't need to have lots of money to pay for consultants. You can have somebody who can afford very little, but still be part of the project. And then the trust means that when you buy the credit, you can see where it's coming from. It's not just saying, here, I paid £5, my flight to New York is covered. You want to say, well, why is it covered? And on the other side, you want to ask who's buying these credits and why should they be allowed to buy credits? Is it fair for Shell, for example, to buy lots of credits and claim our oil is green because we bought credits? It somehow doesn't seem right. So I'm not going to go into the philosophy of that, but certainly we want to know who they are. And then you can make your own mind whether it's fair or not. So we set up the Cambridge Center for Carbon Credits just about a year ago to establish a global framework to issue trusted carbon credits for independently verifiable and accountable nature-based solutions. So all this stuff in red is basically the highlights of what we try to do. So we wrote this sentence about almost a year and a half, almost 2 years ago now, and we haven't had to change a word of it. It's really exactly what we're doing. And this afternoon at 4, we'll be having this launch event where the first success is for us to convince students of Cambridge that these carbon credits are trusted and that they can be independently verified and they're based on nature-based solutions. And it's global in the sense that we'll actually have a representative from Sierra Leone, somebody from Cambridge, and money flowing from essentially Cambridge to Sierra Leone, right in that route. So, which I think is, it highlights all these 4 aspects of our aspiration. Okay, so what's the framework? What we want to do is to start with what can we trust? And what we can trust is what we call trusted primary observations. Typically, these observations made from space, right? So you have satellite images, which we believe cannot be tampered with. But alternatively, you could have observations made using crowd sensing, like an iNaturalist or something like that. And by doing that, we're able to get to know what's happening on the ground. Like I showed you earlier, there's a forest that hasn't been cut down. That's primary observation. The next thing we want to do is to come up with what we call peer-reviewed algorithms. These are not proprietary algorithms. These are open algorithms. Anybody wants to look at them. And that allows us to use what's called counterfactual reasoning. Why is it counterfactual reasoning? What we want to do is to say, this forest is still here. If action wasn't taken, it would have gone away. So it's like this hypothetical, right? We don't want the forest to go, right? So that counterfactual reasoning is saying, if we didn't take action, something bad would have happened, because we don't want bad things to happen. Now, on the other hand, we can also use normal reasoning. There were no trees 2 years ago. Now there are trees. We give you money, right? That's regrowth. But as Anil is explaining, when you have a house on fire, right? Putting out the fire, preventing deforestation is far more important than growing more trees, but that takes 100 years, right? Or whatever, 80 years. So we want to start with these observations, get these algorithms, and then you create these carbon credits. It goes into a decentralized marketplace. And the decentralized marketplace really means that no single entity controls it, because when some single entity controls a market, then it's vulnerable to tampering. Then you can change the prices, you can do stuff. And so we don't want that to happen. And then the vision was that, depending on what credits are being sold or not sold, we can say, well, we need more observations. We can go back and say we need more observations there because nobody believes those credits or something like that. Now, we actually haven't done that, but this was our framework from the beginning. So we have this vision, and now we have to operationalize it by doing getting access to trusted primary data, by coming up with algorithms, and then coming up with the credits from those algorithms, and underpinning all of that in computer systems. So before we go any further, are there any questions about any of these things that is said so far? All right, so let me just move on then to this, what the system looks like. This is really quite annoying. Okay, let's zoom in system. Oh, there you go, went away, very good. So what we have over here, and for people who are online, I'm going to use the numbers on the screen, so just bear with me. In the first step, which is number 1 over here, we have these nature-based solutions on the left. And what we're doing is we are verifying that they own that, they actually are responsible. But I don't want somebody to say, here, I own this plot of land, in Brazil, so pay me, because they never owned it. How do you know they own it? So we need to have that verification done. And we don't do that using computer systems. We rely on governmental identification as we normally would. Once you've done that, in step 2, we have these trusted primary observations from satellite or mobile phones or just meters. And these observations are put into cloud storage, right? And so here we're showing cloud storage in step 3, and that can be huge. We'll talk a little bit more about the scale, but we're talking petabytes over here, right? So because satellites certainly gather huge amounts of data, and then from these cloud storage, we're doing some analytics. We're putting some hashes of the cloud storage into the blockchain over here, and there's just the blockchain shown over here, because that is to give us trust that the observations have not been tampered with. So that's this arrow number 4. And then we extract from the cloud using number 5 some information, and we use analytics, shown with this brain over here. And number 6, we're putting these information back into the blockchain, saying this is the number of credits that should be issued. And then in number 7, we have these credits being bought, put into marketplace, and then number 8, they're bought, right? And that's this slide we did again about 2 years ago. It's basically what we've done. So what we've done so far is we have data from the nature-based solution is the one that's in Gola, announcing data today. And that goes, and it's verified by the World Society for Protection of Birds, RSPB. We have Earth observations based on Landsat. We have cloud storage, which is the room next door. It's not in the cloud, actually the server next door. And the analytics algorithms are being done by Tom Springfield and his team. And we're using the Tezos blockchain. And today we're getting the purchase. It's not fully done, but the purchaser is the University of Cambridge. So it goes from Cambridge to Gola. It's all on this one side. Right? So that's the picture. So looks good. And are we done? Right? And the short answer is no, we're not done. And what I'm going to go is a little bit under the covers to see what's happening. So what would it look like if it actually were done? We could have a purchase GUI. It looks like a shopping cart that you would get, you're checking out from Amazon or something. Here are the partners. You can't see it. That's okay. The debt column is the partner. It's what the project name is, and then you have some kind of credits that are available and the quality of the credits. Does it have high biodiversity? Does it have low biodiversity? Does it impact fertilizers, etc.? How many is available? And you go buy it, and that's the shopping cart. So why can't we have that, right? And the answer, it's because we don't have all of the underlying machinery. But when we do this, we hope to have it. So let's start with primary observations. As you already mentioned, these are going to be satellite imagery, and I'm going to focus right now on avoided deforestation because that's what we have most competence at the moment. And so that we wanted to take deforestation using Landsat models. JEDA is the LiDAR thing that Amelia mentioned earlier. And so we're going to use these as primary observations. And then we want to do this deforestation detection using these counterfactual algorithms. And at the moment, we have algorithms for additionality and impermanence or permanence. And we have something for leakage we're not very happy with. And then we have the so-called co-benefits, which we have no algorithms for, but we're working on it. So biodiversity, justice, and local livelihoods. So those are open areas. So if you want to look for a research project that is challenging and can be really, really helpful, we want to say, how are local livelihoods affected by for avoided deforestation project? How do you even begin to answer that, right? And that would be something that's interesting. Then we're very interested in talking about it. So briefly, what is additionality? We have what we call a treatment where this project is being run, and then we have the counterfactual where the project is not being run, and the difference between the two, which is this blob over here. So in the counterfactual, we had no deforestation except in this big blob over here, small blob over here, and so we think that would be the additionality is available to you. And so we talked about this, so Tom talked about this, I'm not going to talk much more about it. And the easier way to look at it, another way to look at it, the rate of deforestation in the counterfactual area versus the rate of deforestation, the line above in the project area, and the gap between the two essentially is the gain from additional gain from having the project. So that's the idea over here. Leakage, again, Tom talked about it. The leakage is a problem that when you have no deforestation here in upper parts, but we have a dotted line, and outside the dotted line, we have deforestation just adjacent to it, then there's no net gain. You're not actually getting any benefit at all because you just displaced it. So that's local leakage. And then global leakage means that it looks like we have additionality, but in fact, what's happened is that we just did the deforestation in a different country. And if that happens, then we're really out of luck. How do we know, right? So you have somebody who wants to buy lumber. They say you can buy it from this forest nearby because it's protected. That's all right. We buy it from Malaysia. Okay? Then what? So we don't know. Again, that's another supply chain issue. Actually, it comes down to what you say. Can we trace a supply chain of lumber or other forest products back all the way to the point of consumption and say that, well, it was not happening here, but it happened somewhere else, and so there's no net benefit. So it's a tricky problem, actually. Okay, and so in permanence, we want to have a permanent outcome. So let's say that this is the avoided, the upper line represents the avoided deforestation. So rate of deforestation slowed down. What we'd really like to have is that at the end of the project, the deforestation pretty much stops. And of course, the counterfactual keeps going down. So this green area is the amount of permanence that we have. That would be ideal, but in fact, we will not have that. And so what we do is we value permanence using this sort of this formula over here. And again, in the interest of time, I'm not going to go over in much detail, but we look at the social cost of carbon being the value of carbon or the damage caused by carbon, and the benefit is the inverse of that. And we look at the social cost of carbon now as the benefit, and then the discounted social cost of carbon as that was released, because it's impermanent, so we have released. This is the cost, and the difference is the net benefit. We divide it by SCC now, that gives us the equivalent permanence. And that equivalent permanence is something that is not quite unique to us, but it certainly distinguishes our approach from the ones that are in the market today. Okay, I've gone through this fairly quickly, so I'm going to stop now and ask any questions about any of these, because I'm going to switch gears in a moment and talk more about the computer science issues. Yes?
Yeah, it was just on the slide where you had the kind of table of...
Yeah.
How will these be priced? Is it based purely on carbon or diversity?
Yeah, that's an excellent question that Onkar is going to answer in his PhD thesis. But the basic thing is that price and cost are related, but not the same thing. So if I were to do an avoided deforestation project in, let's say, Sweden, and I do the same thing in Angola, right? Angola is going to be a lot cheaper. So the costs are much lower because cost of human manpower, person power is lower in Angola. But what should they be priced at? There's some reason to believe that they should all be priced equivalently for somebody buying it, because the climate benefit is identical no matter where you're in the world. And so our current thoughts are to price these at a particular value per token type. By token type, I mean, a credit type, I mean, that if you have high biodiversity gain, let's call it A, and somebody has a B for biodiversity, or somebody has C for biodiversity, somebody has high for social justice, A again. So you can think of AAA as being like best co-benefits down to FFF for the worst. Each of them should have a different price in theory, right? Maybe you don't, maybe you just class them into high, medium, low, or something like that. But this is just like bond traders value bonds. This is a AA bond, or Moody's says a AAA, whatever it is. So those are reflected in the valuation underneath. And so we'd like to have a price that reflects the quality of the credit, as well as the sort of a fairness, and also to some extent the underlying costs. But how this works out, what market dynamics result from it is, I don't know.
Could you ever just leave it to the market?
At the moment, the way it's done is that there is an open market. There is actually billions of credits floating around already, and the prices range from $2 a ton to about $1,000 a ton, right? So same ton.
Yeah. So
if you want to offset, you can buy $1,000 a ton, which is from Climeworks, or you could buy for $2 a ton from some projects out there. So everybody, of course, tries to buy the cheapest one, because all the market right now is a voluntary market, which means that you don't have to comply with anything. So if you buy the cheapest one, you can say I'm green. So as you enter the dividend building, there's a little pub that says you're carbon negative. I bet they're buying $2 tons, not buying $1,000 tons. Right? So that's where that comes from. But it's a good question. I mean, I'm afraid I don't have a good answer for that at all. Any other questions? Yes.
So just still that table. So I think beside the factor like social responsibilities and benefiting the local forests, and other factors that will make the private sector, like the big tech companies, to make them want to buy the carbon credits.
Yeah. Yes. So ideally we would like to have what's called a compliance market. So in the emission trading scheme of cap and trade, there are two markets there. There's a compliance market and the voluntary market. We don't have a compliance market for nature-based solutions for carbon credits. We only have it for energy supply. But I can imagine that might happen, right? Maybe in the next COP, they will do it, or 27, 28, something. I think it has to come. And when that comes, there will be a huge demand for carbon credits. And so in some sense, we're preparing for that. We want to be ready with the science and in the systems when we get this huge market demand and also the credibility that we need. Any other? Okay, so going back to this slide over here, so back to the system over here, I'm not going to focus on the requirements of the system. So, okay, we build it. What should it have? And I'm going to argue that it should have at least the following 6 properties. So first one is that it should support large-scale data analytics, right? Remember, we're going to get lots and lots of data. So we need to be able to work with that. And so the solution I propose is that we should be doing this using essentially cloud computing, right? That's the way we know how to scale up computation with the amount of data without having to own physical infrastructure, without having to invest in having lots of servers. And so at the moment, we're doing everything on sort of a local server, but when you scale out into lots of analysis, I think it will be necessary for us to go into cloud containers. And for those of you who work in cloud computing, there's a very good reason why this is going to happen. As it happens, Anil has gone to give a opening lecture in the cloud computing course, undergraduate course right now. And so we are also invested in it from that perspective. This is something we know, at least Anil knows. Actually, I know something about it because I did a startup in 1998 doing equivalent of Docker. Another story, but yeah, we built these containers at that time. Okay, the second thing is we have this issue of having a global system. Remember, already we have this Cambridge versus Sierra Leone, so there's no single trusted entity. If there had been a single trusted entity, then you could rely on them to do everything. But who would it be in this case? Would it be Cambridge? Maybe the Sierra Leone people say, we don't trust Cambridge to run the registry. They're just going to give them some credit and not pay us. Should it be Sierra Leone? Same problem, right? And this magnifies itself as you have more and more and more people. And so if you want to operate globally without a single entity controlling the network, it kind of leads us naturally to blockchain. Okay? So blockchain has been characterized by many people, including me, as a solution looking for a problem, right? Or a scam looking for a sucker. Okay? Both of these are true. Most blockchain things are bogus. I teach a course on blockchain. Next term I'll be teaching it. So I'm quite aware of the lots of negative issues concerning blockchains. But in this particular instance, it turns out to be just the right fit. And I'll expand more on that in just a few minutes. But certainly it operates globally. And there's no single entity controlling the network. That's by definition what a blockchain does. And so for those people who don't know what a blockchain is, I stole this slide. I copied this slide from Investopedia. It's a digital database, a ledger that's distributed among the nodes of a peer-to-peer network, which means no single person owns the ledger. People have to agree to consensus on what is in the ledger, and this makes it tamper-proof, or at least very difficult to tamper with. So that's the second system requirement. There should be no single trusted entity, and the system solution to that is a blockchain. The third thing we want to have is automated payments. So right now, the way the credit payments are done is that somebody flies into the project site, typically 4 or 5 years after it's been started. They write a report, it's 200 or 300 pages long. And at the end of it, they take a year to write the report, and then they say we issue so many credits. The credits go into a registry like Vera. And then somebody comes along and buys it, and Vera says, okay, we got this money. And a few months later, the money goes to the project. So it's about 4 or 5 years into the project to get some money. And so the first 5 years, they really don't have any money coming into the project because everything is issued post facto, ex post, as they call it. What we'd like to do is to be able to do automated payments, right? We know how to do automated payments. Your bank account gets money every month. when you get paid from a job, right? So all of you get some money coming to your bank account every month. That's automated. It's not coming, little 6 months, 7 months later. So we know how to do that, and it turns out that on a blockchain you can do what I call smart contracts, which are these self-executing contract bits of code, which actually Derek mentioned earlier, which allows us to ensure that whenever somebody buys a credit, instantaneously or nearly instantaneously, a few seconds later, the owner of the project gets the money, right? And I think this is much, much better than the system in place today. Most importantly, there's no way for anybody to bypass the system. You can't have a situation where somebody says, oh, well, I'll buy this credit, but don't report it because it's baked into the blockchain. So it's an automatically executed contract. And so that's why it's important to get it just right. And that explains why Derek is working on smart contracts we can prove to be working properly. Okay, so that's the other thing that we want to be careful about. We want traceability. So I talked about this notion of open peer-to-peer algorithms. So here in traceability, we're saying that we want to vet the credit providers and purchasers. Who bought it? Who provided it, right? And so what I'm showing over here is the smart contract. If you open up a smart contract, it has two bits to it. One is called the ownership, who owns the smart contract, and then the token metadata will come to later. So the ownership data tells us who owns the token. And then we have some off-chain storage here. So, okay, so just focusing on the smart contract, the ownership of the token is encoded in the smart contract. And so we have a very, very clear view of exactly who owns what, and it's not you can't tamper with it. I can't go into registry and say, let's change all of the things that says University of Cambridge or University of Oxford. You can't do that with the blockchain. So that makes traceability very important. And so we have what we call on-chain storage of purchaser IDs. Now, part of this requires us to have digital IDs for all entities, which is a sort of solved problem, but not completely. So there are issues with IDs, digital IDs. But and one of the open issues we have is how do we assign purchaser IDs to entities? How does somebody in Sierra Leone get an ID, right? Because you don't have that, we can't refer to them in the blockchain. So, any questions about this so far? Okay. And I know most of you don't know what a blockchain is, but you can think of a blockchain as having inside it with some entities called smart contracts, which execute whenever certain conditions are met. And inside the smart contract, somebody is the owner. And then we also have off-chain storage, which is basically if you have petabytes of data, you can't put that on chain. For very good reason is you don't want to have petabyte copied over and over again. So you put it off-chain, and what you do is you link with the smart contract to the off-chain storage, and this makes sure that if any change happens in the off-chain storage, it will be detected because there is a hash which is put onto the smart contract. And so this allows us to maintain very large quantities of primary data without having to put them on chain and yet make them immutable, right? So this means that we can also do something clever, which is we can have levels of hiding. So we can say somebody from University of Cambridge can see everything about the contract, but somebody from outside can see only parts of it. And somebody who's not in the UK or not part of the university system can see almost nothing. They'll just know that some UK entity bought it, right? So we can have levels of hiding by having appropriate levels of hashing. So that's part of what what we're building right now.
I have a question.
Yeah.
So what is exactly token data?
What is in the token data? So the token data, so token, think of it as a credit. So each carbon credit will say things like, it came from this project, it was issued in this date, it used this algorithm for verifying additionality, this algorithm for verifying leakage, etc. And the off-chain primary or trusted primary observation is over here, and this is the hash of that observation.
I see. So all satellite images that went into
Yeah,
verifying this.
that's right.
So
Yeah.
anyone can reproduce.
Exactly. In fact, that's why reproducibility is over here. So essentially, you can be very reproducible and verifiable for third parties who are not connected to the transaction. So right now, when you go to your airline, I bought a flight and say, okay, you pay £5, you get a credit. Where is it coming from? We don't know. Can you check it's actually this one credit? We don't know. What's the additionality? We don't know. We have essentially nothing. We have just a complete opacity. And this completely changes around into making it transparent. And it leverages these the design of the blockchain to make all of this happen. Any other? Yes.
Just about the cloud computing side of things.
Yeah.
See, there's a sort of financial and probably a carbon cost associated with that. How does that fit?
It's in about 10 slides from now. Any other questions? Okay. Evolvability. So we want the algorithms to evolve. We are researchers. We're going to make changes to the algorithms. We're going to make sure that we can actually come up with this. So what we do is we actually put the algorithm version also in the soft chain story. So this is the algorithm, this version that was used. And then at that point, we just say, okay, that was what we knew then. This is what the credits were issued. And then we can just version it. And whenever we change the algorithm version, it allows us to self-upgrade the system. So we have this notion of upgradability of these smart contracts is another thing that Derek happens to be working on. So that's where we want upgradability as well. So we want to evolve things. So to summarize, we want to support scalable data analytics. We can do that with cloud containers. We want to operate globally without a single entity with the blockchain. We want automated payments, also with the smart contract and digital IDs. We want to vet providers and purchasers, same thing, purchase IDs will change. We want to have reproducible, verifiable, and we want algorithm over time. So all of these requirements can be met by using a combination of essentially cloud computing and blockchain when properly used. And in fact, that's exactly what we've been doing. And this afternoon, if you do come, then it'll be a small demo of the system showing how it's been put together. And it's not full scale now, but it mostly works. Let's go back to another part of the system, which is the cloud storage. So here I've just circled that. So how do we deal with all the data? And actually here things are a lot less, not as good. Okay, I'm going to talk about the problems we have with the cloud, with cloud storage and the data storage in particular, and then what open issues there are. So when you have lots of primary observations, petabytes of, for those of you who use Google Earth Engine, the Earth Engine catalog has, I think, like 3-4 petabytes of data already. So we want to ingest data. So we want to interface with NASA. We want to interface with cloud, with iNaturalist and other crowdsourcing areas, and essentially get the data from them, ingest it. And to do that, we want to host these standard data sets, and we have to worry about the data being heterogeneous. And it could be private, and we want to have selective sharing. Somebody say, this is my private data, I only want to share some parts of it, but not all of it. So the heterogeneity comes actually in spatial scale. So some of them will be at 3 meter by 3 meter pixels, some will be 30 meter pixels, some will be 2 kilometer pixels. So we have the spatial scale. Some are going to be every 5 to 7 days, like Sentinel. Some of them come at some satellite images come every 3 months or 2 months or whatever. And then the feature space, so some are hyperspectral with 120 bands. Some are RGB and near infrared is 4 bands. So the feature space differs as well. So storing all this data while ingesting all of these and fusing them together actually is a very difficult problem. We need to then interpolate and slice. So interpolation is this fusion where we want to say, I have this 30-day data set, but I want every day what happened, and we can perhaps use AI techniques to interpolate that. And so this is how we fill in the blanks. That might be interesting. We want to do spatial and temporal slicing. Spatial slicing means I just want Sierra Leone. I don't care what the rest of the world, because that's what I'm focused on, or even narrower than that. And temporal slicing, likewise, we say I want the last 5 years. I don't need the last 100 years, or whatever. We want to maintain the data. So once you interpolate slice, we want to have incremental updates as new data comes in. So satellite makes another pass, and then we're able to incorporate the data. So we want this continuous integration pipeline, where as new satellite information comes in, you say, oh, we have better idea of what the credits should be, etc. So we want this for Johan, continuous integration. That's what we want to do. We want to maintain the provenance of all the derived products, so you can work backwards and say, okay, if you got this credit, this is where it came from, this is the trusted primary observations, this is the algorithm, all of this chain to work backwards from. We wanted to distribute this across multiple stores when we maintain it, so loss of a single store doesn't result in the whole system going down. And we want to be able to download these slices to individual people because when they can open. And finally, archival. We want to have the data availability for, let's say, 50 years. Right? We don't know how to build systems in the last 50 years, actually. How do we have access to data that was collected in 1972? We actually don't. It's all on paper tape and punch cards or who knows what. So very little data from 1972 is available today. Can we design a system which actually archives 50 years? We don't know. And of course, we want to have everything, all the computation reproducible 50 years from now. Everybody's going to then use neuromorphic computing with stuff inside your brain, and they have to be able to use plain old CPUs running in Windows 11. How do you do that? I don't know. So these kinds of data management issues are now coming to the fore of what we're working on. And for those of you interested in computer systems and want to contribute, I think there's many open issues that are over here. So that's what I said over there. Just to reiterate, what do you have on the blockchain? We have proof of project ownership. We have the additionality, leakage, and permanent certification. We have tokens to prevent double counting. You get that for free with blockchain, because obviously if somebody owns a token, nobody else can own it, so we can't sell it twice. We can get this global exchange of cryptocurrency to the local currency in that country. So you have the possibility anyway of people being able to get money in their own currency rather than in other currencies. And also automated payments that I already talked about. Briefly, Tezos, blockchain choice. Why did we use Tezos and not Bitcoin or Ethereum? Tezos is a proof of stake chain, so the energy footprint is very small. So you asked about the cloud computing. So the blockchain itself is a cloud computing platform, but the amount of energy used by Tezos is very small. The amount of energy used by the cloud for analysis of the data sets may be higher, would be higher. We haven't actually investigated that. But in the end, we can offset that with carbon offset. It's not going to be many tons. Computing is relatively efficient. We're getting settlement in local fiat. I already talked about that. It has long-term survival and permanence because Tezos is the only blockchain that updates itself every 3 months. It updates its algorithms every 3 months. You might have heard about the Ethereum Merge, which has been going on for 7-8 years and still not quite done. Tezos has been doing a merge every 3 months. And it's on its 13th, 14th merge, I lost track. Derek knows the exact number. But it's all right, I'm not going to put you on the spot.
So the Ethereum merge happened like
2 weeks ago. Oh, the Ethereum, I know, but it merged, but I know, but all of the Ethereum miners are going off and mining other stuff.
Oh, that's true.
Yeah, so in fact, it's a merge that did not reduce the carbon footprint. So yes, I know it merge happened, but I also know that like 85% of the miners are continuing. Very little of the miners have withdrawn from the chain. But anyway, but setting that aside, Tezos is, we think it's going to have long-term survival of the chain itself, and it does these payments to data owners through smart contracts. Okay, so I'm ending more or less on time. So started out with nature-based solutions. I think for people like Felipe, this is the important part, right? We're talking about not carbon capture and in calcium carbonate. We're talking nature-based solutions, which address both the climate and biodiversity crises. And in the end, what we're trying to do is to fund it using voluntary carbon markets. And it's a good idea, but I think many people are waiting on the sidelines. They're saying, I don't really believe this. And on the other side, activists are saying, we don't really believe the people who are buying these credits either, because are they doing a proper decarbonization? So both of these issues need to be addressed, and creating trust in these is critical. So coming with my sort of computer systems hat on, I believe that we can help solve the problem. I've already showed you some of these things from blockchain. This is some research I did some years ago, where we can actually do these kinds of things. And I've hinted at the other open issues in building large-scale, permanent computer systems that are necessary for us to tackle these environmental problems at global scale, right? Not individual pieces, global scale. And we want to do this in collaboration with environmental scientists, and of course, much work still remains. And so, yeah, that's the bottom line. So we have crises, these two crises, and I believe we are working towards a solution. This is our contribution towards the solution of the crisis. And in many ways, this vision is what underpins 4C. It certainly underpins pretty much all the work, not all the work, but most of the work I'm doing in my research, and hopefully is of interest to some of you here. So I'll stop now and I'm happy to take any questions. Thank you. Yeah, next.
Just briefly on when you say there's lots more work still to go,
Yes.
do you have either a rough percentage or a rough timeline milestone where you're hoping to get to a point where you can't say that anymore?
Yeah, so I think in terms of the blockchain, we are pretty much there. I think in terms of the data management, it depends on the scale. So if you're doing small scale, I don't know, 100 terabytes, we can do 100 terabytes reasonably well. We don't need, we have the solution in place today. People are using, Amelia's using it today. It's about 150 terabytes. You can do that. When you get to, I don't know, 10 terabytes, Google knows what to do, but that's proprietary. And I don't think they can do all of these things either, necessarily, what they revealed of it to us. So, yeah, so we have a solution for reasonable scale, but for global scale, I don't think we have a solution. And for global scale, maybe a 40% there. I don't know. I don't know how to put these markers down. You run into problems as you start solving them, and then you say, "Oh, I was really not 40%; it was only 4%." That's a good question. I'm sure. Yes, you.
But this data management role, everyone has.
Indeed, they do, but not all of it. So, for example, this kind of data for decades is a problem that's new here. Reproducible computation with third parties is something that, like if you're a company, you don't have that because it's your proprietary thing. You don't need to have third parties access. And reproducible computation is also in the future, plus what happens with private data, those introduce new complexities that are not necessarily there. Spatial and temporal slicing are probably there for geospatial or spatial temporal databases, but not everything is geospatial. So once you start focusing narrowly into spatial temporal databases, we've looked into that. It's called the Beast from University of Minnesota, for example, and they provide some answers, but really not a lot. They're only a basis to build upon. But yeah, there's a subset of these problems exist in other locations.
So there's no like a centralized place for all environmental data today, where everyone kind of has their own solution, and then I don't.
So I'm not an expert on this, but there are definitely different groups have access to different data. There are at least two efforts to try to bring everything together. So one of them is Google Earth Engine, which is this. Which has been, there's a workshop 2 weeks ago by them, and last week actually, where they talked about their catalog of data products. They have, I don't know, 100-ish data sets that they've collated. They're all open source that they collated from various space agencies and so on. And the other one is a project called Restore, or ETH Zurich, where the Crowther Lab people have collected mostly forest plot data from about 130,000 forest plots around the world. Those are the two collations that I'm aware of. And then, of course, many other ones. I think in Brazil, I forgot the name of the university, but
it's Brazilian.
Yeah. So they have like map biomass and other products which are Brazilian products, mostly for Brazil. But global scale, yeah, sorry.
Yeah, and the ESA, also works on creating collations.
Yeah, but ESA also feeds into Google Earth Engine. So. Yes.
But why you have to ingest all this data inside your software? You cannot just build a bridge and you go inside some. I don't know.
How long will they last? Right. I mean, let's say maybe ESA will last for 50 years, but there are other data sets which may not last that long. So if you want to be able to continue to provide carbon credits, even though the data is not available from the primary source anymore. How many of the web links that you click on actually work 10 years from now? Right? It's the same problem. Yes.
I feel like the blockchain can be very much trusted for the trading,
Yeah.
or the verification part.
Yeah.
Even the state of the art algorithm, they have a bottleneck in accuracies. Is it possible that currently the uncertainties of these algorithms be included when you issue carbon credits?
Amelia is working on this right now, uncertainty in algorithm estimation. Yes, we would like to do that. We have to do that. It's very hard to sell an uncertain thing, by the way. You know, there is 1 plus minus, 0.4. I don't know how do you price that. It can be reflected in perhaps the quality of the credit. It could be a subjective rating. But uncertainty and propagation uncertainty as you derive data products is a very big research area and something that we're engaged on right now. And I mean, that means I don't have an answer. Yes, hi.
I have a practical question in terms of, this is a $2 billion market at the moment.
Yes.
So it's still really small.
Yes.
There's lots of activity happening around it and some expectations that it will become bigger, but still relatively small, say 50 billion. So when we're thinking about these types of resources and the cost of putting them in place, does that have is that having an impact in the sense that people are doing the right things because it's quite a small market? Or is it more important that we use this type of technology because it will be a relatively small market and we don't want it to bear lots of costs because we want money to go in the right place? So I'm just wondering, how much of a constraint is the size of the market now, and how much does the future size of the market matter in terms of what resources are you put into it?
So I have to caution everybody else in the room that Harriet comes from a world where 2 billion is small. For most people, including my bank account, it's a very large number. But yes, you're right. It is a small market in the grand scheme of things. The vision is to try and do this, solve these problems, right? And if you want to solve these problems, we have to go to very large scale. I don't think it's a choice. We really have to go to large scale. So that means this system has to go to large scale. So if it's 2 billion now, my expectation is that that is just temporary. Once you get to the compliance market, it's going to be much bigger. So I think that's it's a bet we're making that's going to get much larger. But if the world is focused on solving the climate and biodiversity crisis, it's necessary that we have a scalable solution, and then we will have these bigger data management problems. So it's not a problem we face necessarily today, but as researchers, we're looking at the problem in 2027, and I can anticipate in 2027 we will need this. So we need to start building now, so we have what we need at that time.
But to put in place this type of technology, it can be relatively low cost, and so that it doesn't impose a constraint.
Yes, right. So, right. So the way we would do it is to build a pilot solution which is low cost and small scale, but then it has no barrier to scaling beyond it. So you put more money, it gets bigger, right? That's the idea. So the whole philosophy of the internet technology is build something which has no limits to scaling. So all of the internet technology is designed in a way, the more money you put it, the bigger it gets. There's no barrier to scale.
But at the moment, there are lots of barriers.
Yes.
It doesn't scale, and also it's high, the percentage costs relative to the benefits is way too high.
Exactly, but that's what we want to change, to automate things, to make it possible for us to scale without having to throw lots of people at it and so on. Yeah, that's the goal. That's why much work remains to be done. That's why we have all these new students, going to do all this work for us. So. Yes, Anita.
Going back to, I think some of the questions people have asked about this idea of creating a new data catalog.
Yeah.
I guess when you talk about keeping this data indefinitely, and it's on needing to keep all the versions of the data as well, that gets very, very large.
Yes.
Relatively quickly. And I think Google Earth Engine is talking about petabytes and petabytes of data, hundreds of petabytes of data already. That is no longer a trivial cost.
Yes. Okay. No, absolutely. So let me try and answer that by pointing to the fact that we don't need to store everything all the time. First of all, when all the credits for a project have been sold, then you don't need a trusted primary data because it's already been sold and not just sold, retired. When they've been retired, it's over, it's gone. So we don't need that data anymore. Moreover, we only need data for those places which have actually got the projects happening. So if there's no projects happening in Antarctica, we drop all the Antarctica data, all the ocean data goes away, etc. So we can shrink down the amount of data to the projects that are either being managed or will conceivably be managed by the system. And so as our footprint expands, then we will need more storage, but it'll be a proportionate kind of thing. There's no point in us storing everything all the time in case there's going to be a project there, right? In the near term, ESA isn't going away and Google Earth Engine isn't going away, so we can trust them. But as we have our own projects, our own project data will need to be backed up until the private under the past. So we are not trying to boil the ocean. We're trying to do it a little bit at a time, incrementally as needed. Yes.
So the best is not important. So it's important just at the moment that we start the project, then after.
Well, we do 5 years before the project for additionality, but yeah, beyond 5 years, we're not doing it at the
But
moment.
if you said that you are shrinking, so if there is an area that you are not supposed to have a project there, then you are starting a project, then you start taking 5 years from then, and then start,
Plus the counterfactual areas which will be in that jurisdiction, so relatively similar. Yeah, we won't need. If you're doing a project in Sierra Leone, we don't need data from in Argentina, for example. So we can do spatial.
Leakage is coming from Argentina.
But that would be different data. That would not be. Yeah, if it's global leakage, yes, that might be a problem. But we try not to think about that. I'm afraid I need to stop because I'm supposed to be in this other meeting 2 minutes ago. So I'll stop here. But if you have any more questions, feel free to send me a mail or stop me or something like that. And I will also close the Zoom over here. So thanks for your participation. I'm ending this call here.